Okay, so Raúl is going to give us a seminar today. Raúl is a postdoc in our group that joined very recently, just before the confinement. Before that, he was in Mexico, and before that, he was in the CNR in Cosenza, and before that, he did his PhD in the University of Calabria, and he's going to talk a little bit about chiral particles. So yeah, please start.
Okay, thank you, Antonio, for the presentation and for the invitation on this seminar. And also, I hope all the people can hear me well without problems. So if it's not the case, you can tell me speak louder or speak softly. So yes, basically, I will talk about optical manipulation, but using chiral particles. And is the title of the presentation, and also is the first slide. We have optical manipulation system with a laser beam. And also we have some image of the chiral particles. As we can see, they exhibit some internal structure, and we can observe this internal structure when we observe the particles between cross polarizers. So this is this image. So now the outline of the talk is introduce the chirality involved in materials and light, and how they will interact to show interesting phenomena. And then these interesting phenomena will be observed through optical manipulation experiments. And I will present some of the recent article published this year talking about the collective motion of chiral Brownian particles. And finally, the conclusions. So we start with the chirality. And the definition of chirality is when one object or structure, it cannot be superposed with a mirror image. So the typical example is with the hands. If we put a line here representing a mirror, one is the mirror image of the other, but there is no mathematical transformation or superposition that can superpose exactly both things. Only they match to this axis of symmetry, mirror image, and is present in the hands and in the molecules and in different scales. So when we have systems like this, we can classify it in two kinds, the left and right. And these are called the enantiomers. In chemistry is the typical notation. And also I present here some example of the most common example of structure, chiral structure is the helix, because it can be turned on the left or turned on the right. So they are two kind of enantiomers, and they are present in everywhere. So as I will try to show you, they are present in matter and in the light, this kind of helical structures. So as I mentioned before, chirality is present at different scales. It's present in cosmology, also in particle physics, in the earth, in the formation of several phenomena, in the plants. I mentioned the hands, the feet. Also in organic chemistry, it gives rise to different compounds, which results in different properties of the objects. And also it appears, as I mentioned, the helical structure, which is chiral, in the DNA chains and also in the RNA. And it's also present in sugars because they are right-handed. And I think amino acids are left-handed. So nature has a certain preference for one of the other of these kinds of enantiomers. And it's also present in light because as we know, light beams have many dynamical properties. We usually work with a Gaussian beam, but we can also have a phase singularity. This is a vortex beam. And we can also have different properties like different regions of light intensity and dark alternate. This is some kind of laser beam, a diffractional beam. Or we can also play with the phase of of a light beam. So this is one example of Mathieu beams with different phase, and the superposition gives rise to some kind of vortex. So I started my career doing the generation of these light beams. And also one property that has the light is that it carries orbital angular momentum, which is represented here. Here we have different examples of vortex beams with different topological charge. So in this side, we have the topological charge -1, and this in orange represents the wavefront. So as we can observe here, it shows or exhibits the helicoidal structure. This is going in one sense, and the +1 is going in the opposite sense. So we have same topologic charge, but opposite sense. And the intensity distribution is something like this. These vortex are useful to trap bubbles, metallic particles, or hollow spheres. And as we increase the topological charge, the vortex increase the inner size. And also we can observe that the wavefront becomes more twisted. So comparing the topological charge 3 with 1, this is more twisted light, for say something. So besides the optical angular momentum, the phase or the intensity distribution, we also have the polarization of light. So in this case, we have the two enantiomers because we have the right circular polarization and left circular polarization. So in a similar way, we have the electric field with a constant magnitude, and it's rotating, and it describes the circle. So a long time during the propagation, it creates this kind of pattern, an helical pattern. So this is going in this counterclockwise sense, and for left circular polarization, it's going clockwise sense. So it's important to distinguish that we have the two different states of polarization with opposite sense of rotation. So if we understand this, we can observe interesting phenomena because, for instance, I present here the image of a scarab, or I will say a beetle because it's easy. So we have a beetle, and these photographs show how they look without a polarizer, and when we observe these beetles with left circular polarizer or right-hand circular polarizer. So in this case, we can observe that the color is suppressed. They look like dark, and in this case, they look like green. Also, it depends of the wavelength where we are placed. We will observe a more effect or different color as is represented in this picture. So if we have the, depending on the light that we use, we can observe different properties in the same object. And also it will depend on which place in the visible spectrum we are located. So this is the same image representing for right circular polarizer, it looks dark. And for when we observe this beetle with a left circular polarizer, it looks green. So this is because we have a selective reflection, and depending also on the angle of observation, we can obtain different colors and nice effects. So this technology has been applied for different photonic materials, and indeed these are chiral photonic materials. This is an article from last year, and it shows that it's not only dependent on the circular state polarization, but also using linearly polarized light, you can observe different features of the same object. So in general, these photonic materials are of interest for new and emerging applications like anti-counterfeit labels, data encryption, for the aesthetics, beautiful colors, and also for many displays, and because they create super reflective films. And this in particular is the property that we will use for the optical manipulation. Because we start from a photoreactive mesogen. This is a liquid crystal. We start with some liquid crystal in isotropic phase. So it means that the molecular chains are completely random. They don't have any kind of organization. So we add some chiral dopant. In this case, I will represent the left chiral dopant. We can also have right chiral dopant. And then this structure that it was not structure, it was a big disorder. They begin to align in different layers. So if we notice in each layer, there is a small twist. So on each layer, we will observe a little twist. And for instance, when the molecular director, which is represented here, the media of all orientation of these molecules, when it gives a complete rotation, is called the pitch to this distance. So if the molecular rotation spins very slow, the pitch will be very, very long distance. And if it twists very fast, it will be a short distance. So also if we join these molecules, we will observe something like this helical structure again. So that's why it's crystal, chiral liquid crystal. And also it has, this is, by the way, the cholesteric liquid crystal. So when we have this twist in the molecular molecules in this way, is a cholesteric liquid crystal or also chiral liquid crystal. So one phenomena that they show is that when we illuminate this material with a polarized light, they will selectively reflect some kind of light. So in particular, with the circular polarization, we will observe this behavior. When we illuminate with tri-circular polarization on a left material, this polarization will pass through the material without any problem. It will be fully transmitted. And in the case of left incident circular polarized light on left helix, it will be fully reflected. To obtain the fully reflection, we need many of these layers, so many pitch in the structures. If we don't have this kind of structure, like half of the pitch or less, only two of these layers, the light will pass through. But when we have many, it will be reflected. So this is what is represented here. So it's representing the liquid crystal between two planes, and the illumination of light. And this is also the diagram, but we have also the transmission spectra from experimental realization of one of these cholesteric liquid films illuminated with linearly polarized light. So we have this situation because linearly polarized light is the superposition of right and left circular light. So we can observe that one half actually is passing. Here the transmittant is about 50%, and the other 50% is going to be fully reflected. So that's why we can observe this reflecting around this wavelength with this color. And to obtain these photonic band gaps, we need to add some amount of chiral dopant. So in this case, it was 25%, but we can try with different concentration of chiral dopant. So here is the graphic showing a 15%, 25%, and 40%. So they will be around the red color, the green, and blue. So if we have a laser beam in blue, we need to add 40% of chiral dopant, and we will have these photonic band gaps. And this is the condition that describes the photonic band gaps. Is related with the refractive index, ordinary or extraordinary, because it's quite refringent material, and also related with the distance of the pitch. So also another thing is that we can observe that the thickness of the band gap is about 15 microns or 20, something around that. So it's not very narrow. So it's easy to find a nice band gap and place the wavelength inside that band gap. And yes, this is the case when we have the liquid crystal between two crystals, but also we can put this liquid crystal in water and we obtain emulsions. So they will look something like this. The emulsion of liquid crystal have a different molecular configuration. This is something that we will observe later. So here we have the example of two configuration, bipolar radial. And this reactive messaging has the characteristic that it can be photopolymerized. So when it's irradiated with UV light, it will pass from liquid phase in emulsion into a solid phase. So we can create these solid spheres with the internal molecular architecture, and we can also play it with the proportion of the cholesteric pitch compared with the diameter of the particle. So in this image, I'm representing when they are comparable. This is one pitch is almost equal to the size of the diameter. And in this case, the pitch, cholesteric pitch, is very small compared with the diameter. So it means that we have many of these layers, and we can observe actually these layers through the microscope. Here, there is an image of the 10 image transmission electron microscope. And also, when we have one of these spheres and we cut in the half, in the same image, we can observe this modulation in the refractive index. So it looks like concentric spheres. And as I mentioned, or I didn't mention, but it's written here, the diameter of the particles is about 1 to 15 microns. So we have a big range to create this. And as I mentioned, here is also a 2D representation of this image. So we have concentric layers with different refractive index, and these are spherical layers. So as I mentioned, we have this confined molecular change in the emulsion. And as the image that I presented before, we have two main kinds of configurations. We have the bipolar and radial. And we can have also many configurations in the middle, but which correspond to some radial with some defect, or the origin of this radial configuration is displaced to the surface, or it has some perturbations. So this is the representation of the internal molecular structure, and this is how the particles look through visible light. And as we can see, there is no apparently any difference between bipolar and radial. And with this, we can also see some kind of shadow, but it looks the same. So to observe the internal molecular structure, we need to observe the particles between cross polarizers. So between cross polarizers, the radial configuration will look like this across multis, and the bipolar will look like an elliptical spot of scattered light. So again, the configurations in the middle are something just in the middle between the cross and these configurations. So for the experiments, I will focus only using these kind of particles with radial distribution. So in many experiments, we won't observe this spherical structure of the particles, but we will observe the cross pattern. So here I present some example or videos showing how we obtain the particles and how they reflect the light. This is on the reflection mode microscope. We can observe how they focus the light, and this is transmission. We can observe the cross pattern. And this, which is not a cross pattern, is something like this radial configuration. So when we have something like this, which is not a cross configuration, they will reflect the light in a specific direction. So these are particles swimming in water, and we can observe how they reflect the light along a cone and also along a ring of light. So we illuminate and they reflect only along this molecular change. So it's highly directional reflection. So as I mentioned, we can obtain radial configuration. This is in transmission, in reflection mode observation. And these are obtained when we combine the cholesteric liquid crystal with pure water. And once we photopolymerize, we obtain these solid particles. And again, here we have a picture of the solid particle reflecting light. It corresponds to this. And for the other kinds of particles, which is not radial, but they exhibit a selective reflection in one direction. They have this internal molecular configuration, and this is due because we combine not just pure water, but also some surfactant like polyvinyl amide, impurities, soap, or different kind of things. So again, we obtain the solid particles, and when we illuminate these particles, they reflect at one specific wavelength, one specific color, and it will be in one direction, like this line or these kind of cones. So for the moment, it's okay. No questions or no problems. So, okay, I will assume.
No, I think there's no questions
Okay.
for now.
I will assume everything is going well, so I will continue. Now that we are experts in chirality with materials and light, and we create some particles, we can perform some optical manipulation experiments. So here I present the control strategies and selective tuning to perform the experiments. So as I mentioned, we can play with the size of the particle, with the proportion of the helicoidal pitch, and the radius of the particle or diameter. And basically, we are playing with the reflection of left circular polarized light because we have left helical structure, so they are left particles. So in one case, the reflection of light will be very low, and in one case, it will be very high. So as is represented here, we need only 4 or 5 layers of this concentric spheres to have a very high reflection. Is the super reflection that I mentioned before. And when we have only 1 or 2 layers, the reflection of the left circular polarized light will be very low. So most of the light will pass through this material. And this is the, this curve is the reflection is given by this equation and is related to the refractive index and the wavelength that we are using to illuminate this particle. So also, as I mentioned, we can play with the concentration of chiral dopant to place the photonic bandgap at one specific wavelength. So we can have a photonic bandgap near infrared or in blue, green, red. So depending on the laser that you have, you add some percentage amount of chiral dopant, and then you obtain the photonic bandgap, and then you illuminate, and you will observe this selective reflection. And also, I didn't mention before, but when we pass from the liquid phase to solid phase, the internal molecular structure obviously remains, and also the position of the photonic bandgap. So practically, the optical properties of the molecular structure remain, and we can use it in both in liquid phase and solid phase. And also, we can also play it with the polarization state of light from linear, elliptical, or circular polarized light. And we mainly focus in the 2 opposite circular polarizations. But yes, we can also use elliptical polarization or linear polarization. So the basis of the optomechanics is that light and matter are 2 chiral entities interacting, as we saw. And the chirality breaks the symmetry in the transfer of angular momentum of spin. This is not very intuitive or not so clear. So that's why I present this diagram. So we know that in this case, we have a normal mirror. So if we have incident light with a spin positive +1, one part of the incident light will be transmitted This is usually a negligible term. And the other part of the light will be reflected. So in a normal mirror, what occurs is that if we have incident plus spin, it will be reversed in the direction, but also the spin will change to plus to minus. So it will change the state of polarization. If we have left incident circular polarization, it will be reflected to right circular polarization. So when we have +1 and -1, the optical torque due to the radiation is 0. But in the chiral mirror, we don't have this behavior. If we have incident plus polarization, again, we will have one negligible term that will be passing to the material. And also we will have the reflected light, reflected wave, but in this case, the spin will not change. So we cannot perform this subtraction. These are terms that are adding between them. So we will have a contribution in the optical torque. So it will depend on the reflectance of the material on the state of polarization given by these two phi. So here is represented the right circular polarization, linear polarization, or left circular polarization. And these are the reflectance, the power of the light, speed of light is here, and the angular frequency. So in a chiral mirror, we have this asymmetry, and we will observe some transfer of optical torque. So that's why I represent. And here I present the first experiment that we saw using these chiral particles. As I mentioned, we will use cross polarizers. So we put in our optical tweezer systems. And one feature of these optical traps is that they are very low numerical aperture. So it means extended traps, not very focused, not oil immersion. And again, we use left material, so the right circular polarization will pass through the particle, and the left circular polarization will be fully reflected. So we have this photonic bandgap to match with the wavelength of a laser, which was 448. And when they match, and we have these particles, we observe this behavior. So it's important that they match. It's something like we have a knot and a screw. So if they match, it will penetrate. If they don't match, it won't penetrate. So this is the kind of effect that we observe. It's some kind of Janus because it shows two phases. It has some attraction and repulsion, as we will see here. In this region is the illuminated beam, the beam spot. So we start with left circular polarization, and in this case, we can observe the repulsion of the particles from the light. This is in real time, so we change to right circular polarization, and all the particles are attracted. So we can move the particles, these also will be attracted, and when we change again the polarization state to left, they will have repulsion to the light. So it's interesting. So actually it works, the selective reflection, and we calculate the optical force. We have the gradient force, the scattering force. And what we have here is the representation of the Gaussian beam profile in gray. So for the case of right circular polarization, the reflectance is almost 0. So it means that the particle will be fully attracted to the maximum intensity of the light. So it will settle in an equilibrium position state. And when we change to the opposite circular polarization, this is no longer an equilibrium position, but instead it's a non-equilibrium position, and it will try to away from this maximum intensity. So the simulation worked well with the gradient force. And also in the scattering force, we can observe this behavior that is always pushing to the particles. But when we compare the right circular polarization with the left circular polarization is very strong. So compared with this, there is no comparison. So it behaves like a metal particle, which that's why they feel some repulsion to the light. And this is another case when we don't have as being spots so small. In this case, it's bigger. And again, we can observe with right circular polarization is attracted. Left circular polarization, it feels repulsion. We can also observe that this bigger particle is more evident the effect, but also in the smaller particle, it shows the same kind of interaction. A little of repulsion, but it's more evident here because, of course, it has many more layers. So, okay. As I mentioned before, we can also not only focus in the center of the bandgap, we can also make a little shift with the position of the incident light with the position of the bandgap. So if we are in these gray regions, we will have a transmittance that will be changing, for example, ranging from 90%, 80%, 70%, etc. So when we are in the middle, we have that 50%, but when we are in a slightly shifted position, we have a full range of transmittance. So this is the equation that we use for the gradient force and the scattering force, and everything is represented here with the reflectance value. So changing the reflectance value from 50% to 90%, it will show that behavior that we saw in the previous graphic. And yeah, also one important thing is that you don't only have to use circular polarized light, you can use linearly polarized light because you have, we know linearly polarized light is a superposition, 50% left, 50% right. So it's some kind of racemic light. And we can also use unpolarized light and we'll observe some effects. So I mentioned this because I think most of the people still don't understand what means this, because they say, oh yes, attraction, repulsion, it's optical twisters. And when the particle rotates, it's like, yes, but you are transferring orbital angular momentum. And no, we are using only a Gaussian beam. So yes, I will show, these are like the same graphics we have at a certain reflectance value about this position, 80% transmission, 20% reflectance. We will have, in one case, the stable optical trapping. And for when we increase the reflectance, we will have the repulsion. So here is attraction, here is repulsion. And we saw that in some value in the middle, we have some bifurcation. So in this case, it was stable equilibrium, here unstable equilibrium, but something in the middle will not be just one single line, but it will split into two lines. We have these bifurcations. And what it means is that when we increase the size of the particles, we will have more than one equilibrium position. So as is represented here, if we have small particles, they will be attracted to the maximum intensity of light. And when we increase the center, here is almost stable, but when we pass to bigger particle, now the equilibrium position will be settled here and here. So we have two equilibrium positions, and in the maximum intensity is now an unstable equilibrium position. So it represents that small particles will be attracted in the maximum intensity region, and bigger particles will be stably trapped in a ring region. So again, this is representing, this is small particle, this is bigger particle, and this is what we saw. We use a Gaussian beam illuminating our chiral particle, and it starts rotating. And also when we use linearly polarized beam and unpolarized light. So the particle will rotate as we were transferring optical angular momentum. So actually the particle was describing this behavior. And it was continuous, kind of continuous. So yes, I analyze, I obtain the trajectory. This is the trajectory is a nice circle. And also this is the evolution and time. And we can see the amplitude of this oscillation in X and Y. So it's important again to notice that the particle orbits with linearly polarized light. So it's not transfer of orbital angular momentum. And yes, again, when we try with the different state of polarization, left, linear, and right, we observe this behavior that I mentioned with the optical torque. So in the case of left circular polarized light, we observe that actually rotates, describe these orbits, and is faster. So it's represented here, the orbit, the amplitude and frequency, the oscillation. Then with the same particle, we change to linearly polarized light, and again, still rotates. So it's represented here, a smaller orbit size, and also the frequency changes in red, but still rotates. Now we will change to right circular polarization. This is a left particle, so what happened with the right circular polarization? The light passes through the material and we have stable trapping. So in this case, there won't be any oscillation, and this is more Brownian fluctuation, but stable trapping. So in normal particles or birefringent particles with right circular polarization, it will rotate in the opposite direction, but this is not the case, and this is due to chirality. So again, another example is, let's try with the two counterpropagating beams. It's something that similar to what did Arthur Ashkin, rest in peace. And also it used two similar beams with the same focal length. And as we expect, if the force balance, the particle will be stable trapped in the middle of this configuration, because both particles and the force are balancing here in the middle. But in the case of chiral particles, when we have this kind of system, we won't observe any equilibrium when we alternate the polarization states. So I present here, when we have, yes, these configurations, on both sides we have same polarization, we will have this balance. And when we have this cross polarization or combination of linear and circular polarization, we will observe some interesting effects. So in all these experiments, they were left-handed particles. And this is what represent right circular, left circular, and LP is linear polarization. So what we observe, as I mentioned, in the case of identical polarizations, the particle is trapped in the middle, there is no movement, no rotation. So it's really boring. So also again, important to mention the power on both sides was the same, and these are the parameters, size of particle, beam waist, the size of the pitch, wavelength. So everything is in equilibrium. When we have left linear polarization and right circular polarization, we observe a little displacement from the center of the configuration. So we have this small displacement compared, and also, if you can observe, there is some rotation. And it actually, as you can see here, is half of the maximum rotation. And the maximum rotation was observed when we have the two opposite circular polarizations. So it's rotating fast compared with this. And it's also very displaced from the equilibrium position. It's no longer in the center. And this is because the imbalance between the optical forces. So this is a diagram. Of course, we can, it's obvious that if we have a system like this with a mixture of left and right circular particles, they will be separated on different sides. So if we have a mixture, we can use this technique as application to separate enantiomers. So here is an image sequence showing how, when we have the same polarization, they are balanced in equilibrium. And as we change the polarization state, passing from left to right circular, the particle will have this displacement, which was non-neglectable. It was about 13 microns. So it was very obvious, very well separated. And this is the behavior between the oscillation, the stiffness, of course, with the stiffness of the trap. In the case of opposite circular polarization, the particle was moving more. It was less trap. In the other case, it's very similar. And also we saw the frequency is more evident in the video that when we have opposite circular polarization, the particle will rotate faster, almost the double that when we have linear polarization and right circular polarization. So also, this is something that it wasn't published. We tried with a left particle with a radial defect, and we can observe also with the same configuration, but bigger particle, we can observe this internal structure. We can observe this defect. We can observe how the particle aligns with the polarization state. Okay, sorry. So, yes, the particle is rotating along this axis. And it's not so persistent, not so continuous, but yes, it's rotating. And it has one orientation. We distinguish the orientation because this linear defect. Yes, so it's clear. When we use right circular polarization and linear polarization, we observe a different orientation and how we start to oscillate. And also now the rotation is in different directions. It's not from up to down, but is lateral. And here was actually pumping the water. That's why we see things moving around, because it's pumping the sample. And this is, again, a movement more persistent, more continuous. And also in the case of same polarization, we expect that equilibrium condition, no movement, but I think the defect breaks the symmetry and it gives a different movement. So we have different orientation, we have some translation, and also some little rotation. So this is a very complicated configuration that exhibits, at least exhibits how the particles align with the field. And it tries to find an equilibrium position, but never finds stable equilibrium. Okay, so with this configuration, we observe many different behaviors depending on the polarization state. And also, here I present the image sequence when we have one particle in blue, is represented here, is only fluctuating about the equilibrium position, about the x-axis. But in the case of two particles, we observe this lateral oscillation, which is a very big displacement compared with the case of singular particle. So it has a displacement of almost 2-3 microns. And this is due to some interaction or optical binding between these two particles. So here is the video. We can see how they kind of are rotating, interact. And in time, they have this lateral displacement. This lateral displacement is also going down, a little going up, and also down. And it's not periodic, it is kind of random oscillation. So this effect is not well understood. That's why it's open problem. It's related with optical binding between chiral particles. And yes, as I mentioned, it's not kind of periodic, but yes, it occurs very often. So this gives rise to the next experiment. So we know that particles interact, but what happened in the case of more than two particles. So far it's good. Okay, I will assume that yes. So we pass to the collective motion of chiral particles, or these were chiral particles, and the difference is that we were using circular polarized beam, and in this case, with respect to the former experiments, in former experiments we were using only left-type particles. So with this we have the reflection, and in this we have the optical trapping. Normal optical tweezers, but for this experiment, we could get the other kind of chiral dopant. So we have right type particles. So it has opposite helix, and also it will show opposite behavior. And also we use particles without, with no helical structure. So these in principle are achiral, but I prefer to say non-chiral particles. So this is like control particles, because they don't should exhibit any difference with left and right polarization. So yes, spoiler alert, when we have left circular polarization on left particles, they will rotate and they will create some angular momentum in this direction. And when we have the opposite case, with right particles and right circular polarization, they will rotate in opposite direction, and the angular momentum will be pointing in the opposite direction. So in the case of non-chiral particles, they will only interact with the light as regular optical tweezers. So no rotation, no angular momentum, no exciting dynamics. So what we saw is that here is a set of frames at different time intervals, 10, 20, and 30 seconds, and each frame shows the last 15 steps in time. And we can see how, in this case, the trajectories are showing some kind of some arc. It's not a fully rotation or full circle, but it's some arc. And in the other case, when we have this no interaction, they behave more like Brownian particles. So again, in the opposite case, when we have left polarization, right particles, the behavior reverse. So when we have right circular polarization on right particles, now we will have the arc, or this kind of part of the orbital motion, orbital trajectory. And just to show this image, I will present here the videos. So in this case, we will observe rotation in counterclockwise direction. Topic works, yes. So at the end is Brownian motion, but if you do the statistics, you will calculate this preference to rotate in this direction. So it's not a full circular trajectory, is not well behaved, but is there. Here is evident. That was very clear. Yes, so they are rotating. We can say, yes, they are rotating in this direction. Sometimes they rotate here, but after that, they return that. And this is the other case with left circular polarization on right particles. They behave like, yes, like Brownian motion. So no big displacement. They are in the same position. They are actually fighting for the center position. So there is no interaction. Yes, in this case we have, yeah, I think this video was with this. Yes, because we have left particles and left particles. So yes, in this case, we have Brownian motion, so we don't have this organized collective motion. They are just fluctuating around. And yes, you might say, here you have 3 particles and you are showing the video of 4 particles. Yes, it's true, but as we will see in the next graphic, it's not relevant at this moment. It could be even better to have more particles and show that in this moment they will behave in the same way. So in this case, also we saw this Brownian motion, but in this case, we will expect to observe collective motion in the opposite direction. And also we can see the distribution here. They are very focused in the center, and here they extend the range of movement. So something is happening there. Yes, as you can see, they are describing these kind of arcs, trajectories, which are not perfect, but still are there. And that's why we calculate the angular momentum. So we perform the analysis of the trajectories, the mean square displacement. We observe these 2 behaviors. In the case when we have this rotation counterclockwise, the mean square displacement increases and then somehow it starts to oscillate. For all independent particles, they show more or less the same behavior. And the mean square angular displacement, it has also some kind of oscillations. In the other case, the curves are smooth. They don't show this maximum minimum. They just settle in one value and they fluctuate just a little. And this is what I mentioned. It doesn't matter 3 or 4 particles. Practically, they behave the same. In this other case, they kind of oscillate, but not so much compared with this. In this case, it was more evident, so it shows different behavior. In the case of right particles, we observe same behavior, but opposite. So in this case, with left circular polarization and right particles, the curves are smooth. In the case of right circular polarization and right particles, when we have these rotations, we have again the maximum minimum at different scales. This is a different scales because the particles were not exactly at the same size, so they are kind of different. And also here, with the mean square angular displacement, we don't see any trend. And in this case, we can observe an oscillation between maximum and minimum. So, yeah, in the case of non-chiral particles, we don't have any trend, any oscillation. They are just there, optically trapped particles, so nothing exciting. So besides this analysis with the graphics and the angular momentum, we try to perform numerical simulation or try to calculate the behavior of these particle trajectories. So our collaborator from UNAM, theoretical collaborator, used a Langevin type model equation when we use the coupling of different force. This was the chiral coupling or propelling force. Here is the term representing the optical force and some white noise. So, and also this is the rotation of the swimming direction. Here we have the angular velocity and the displacement of these swimming vectors. So we have a competition of these, the optical force and the Brownian forces. And when we have this chiral coupling, it will dominate over the Brownian effects. But they are always there. There is only just one competition. When we don't have this chiral coupling, it will dominate, yes, the optical force and the noise. So we will have the angular distribution, the swimming speed, the diffusion. And when we consider the movement only in two dimension, this equation becomes something like this. And when he put these equations in the numerical simulations, he obtained something like this. In the case of strongly particles for different values of Peclet number, going from small to bigger Peclet number, he observed that in the case of strongly trapped particles, they perform really nice circular orbits. They start in a random position and they eventually perform the circular orbits. In the case of middle trap particles, so not so strong optical trap particle trap, which is represented by this coefficient, they perform still these kind of orbits, but they are not highly concentrated in a region. They spread in a bigger distance. And in the case of weakly trapped particles, they exhibit the Brownian motion. So in some cases, depending on the Becklet number, they will still kind of perform this orbital motion, but for low Becklet number, they will show a pure Brownian motion. So we have always this competition, and in one case, one dominates over the other. And using the experimental values, he also was able to reproduce the behavior. In one case of circular polarization, it shows Brownian motion and the mean square displacement was smooth. And in the other case of the right circular polarization with right circular light, which correspond to the orbits and the trajectories, he obtained something like it was a closed trajectory and bigger size compared with the Brownian. And when he performed an analysis of the mean square displacement, he also observed these oscillations for each one of the particle 1, particle 2, and particle 3. So at the end, he was able to reproduce the observed behavior only using that simple model and some experimental values. So now for the conclusions, we use chiral light. We can observe different chiral optomechanics. We observe the Kainos-Young particles. It could be used for sensor devices. We observe the emergence of collective motions. We can create new materials using spherical chiral microparticles. This is an example, for instance, of the sensor devices. We can create or play with the photonic bandgaps and create tunable light sources. So yes, here was the rotation. I only thank to my other co-authors and also for the funding, very important. And thank you for your time.
Thank you, Raúl.
Thank you.
Is there anyone who has any questions? I do have a couple. So I think the first one is like, so how do you freeze these particles? What is the process? So I think you mentioned you make an emulsion.
Yes.
Is that by microfluidics or something?
The ideal will be microfluidic, yes, and it surely works. But the thing is that no, we didn't use microfluidic. It was only put a small drop in water, pure water, and then it was shake. Only shake with a shaker. Yes, we control the frequency, the time, and also it was a certain temperature. This liquid crystal is very viscous, so it needs to be in a fluid phase to form these microspheres. They form in a natural way these microspheres. We put in a chamber and we irradiate for the photopolymerization. So it was a process about 6 hours irradiating, and then it freeze and it was solid. So it was very easy.
Yeah, but I think I was more. I think I was more interested over. I mean, I think that I wanted to know how you make the spheres, because I didn't know if it was like just shaking, like making vinaigrette, or with microfluidic.
We tried also with Achieve and microfluidic, but because it was very viscous, we were not able to work with this. It requires a special device. Yeah, and also.
Yes. So in the. Oh, okay. No, just so when you have this rotation in the Oh, sorry. Wait, no. Mattia has some questions, so maybe we can just unmute him. So I think you have
Can
to
I?
unmute yourself, Mattia. Yeah.
Yes, yes, yes. Can you hear me? Okay. I have two questions. First, Raúl, can you go on to slide 14?
Yes.
Or
Yes, of course you will ask about this.
no, 14, not 34. Actually, it was not that.
I'm sorry. I can find the 14. What was?
14. Okay.
Yep.
Okay. So here, actually, I have some question because basically on that you told me that of course it changes the how the interplay within the chirality of light and the chirality of the mirror material can affect how light is reflected and transmitted. Actually, my question was, here you denote another reflectance, right? Which is the reflectance for the particular process.
Yes.
And I wanted to know, actually, this reflectance is higher or lower than the one with a non-chiral mirror? And what about the transmittance?
Yes, it's a very good question. And yes, it's a very important point. Yes, these reflectance are not the same. In this case, is normal reflectance. In this case, it's only for the case of left circular polarization. So we split this reflectance into two, into left reflectance and right reflectance. So that's why is denoted with plus and minus. And yes, of course, is telling you that they, in one particular case, when you have both of these, they will be these normal reflectance. So they are smaller in principle.
Okay. Okay. So the radial force is smaller, but you gain in torque. This is basically the.
Yes. And
Okay.
yeah. And also, in principle, we can say the reflectance is going to 0 to 1, but 1 corresponds to the 50% for left circular light. The other 50% is for right light.
Okay. Okay. Then I had. Thank you very much, Raúl. I also had another question, if I can.
Yes.
On slide 26, this time, which is basically on the. Maybe that is just me. Okay. So here when you say that so the point you're saying that when you at least when the polarization of the two lights that you used to trap the particle were different, you have a force which is non-zero. So the system is not in mechanical equilibrium. So does it mean that you observe a drift in some direction? I mean, if you continuously observe the particle, I guess that if you have unbalanced forces, it will be pushed to one side of the channel. Is it right?
Yes, exactly. That is what happened. And to explain that, notice in these spots. So
No, okay, because here it looked like it was trapped. This is what I'm saying, because it's true that it shifted the position,
yes.
but it doesn't look like it's still shifting.
I mean, the particle is trapped, and they might be a little drift, but in general, we always found an equilibrium position. It was
Okay.
but yeah, that was also unexpected because we only expect that particle will move and never stop in one direction or the other, but we always found an equilibrium position.
Okay, this is interesting. Do you have any idea on why is that?
Yeah, actually, yes, but I didn't explain.
Okay.
Yes, we found that there is some potential.
Okay.
With this kind. It's a kind of washboard potential.
Okay.
So
Yes.
it will be it will have one inclination on one side or the other when we reverse polarizations, and when
Okay.
they are the same, this becomes flat and without inclination.
Okay.
So the particles distinguish this potential, and it will pass from one minimum to the other, but this inclination also is not constant, it's not infinite. It will tend to slightly change. So that's why in some position it doesn't have the enough energy to pass to the
Okay.
other.
So basically, this is why because basically the particle gets trapped in a metastable minimum of the washboard potential.
Exactly.
Okay.
And
Perfect.
it will depend of the reflectance. Yeah.
Okay.
The reflectance
Perfect.
will give you the
Oh,
inclination of this.
what did you say? Sorry.
Yes, the reflectance will give you the inclination of this washboard potential. So
Okay.
how to think it will be trapped in some position.
Perfect. Thank you very much, Raúl.
Thank you.
So, but to continue with these questions, I would expect this to be kind of modulated by a Gaussian, no? Because eventually the beam is also weaker farther away from the center of the two, no? Of the two beams meeting point.
Uh, yeah, it's true, but it's something that is represented here. When you have here one Gaussian and here the other Gaussian, they create this region in the middle that becomes very stable, and it helps you to trap here. Because you can also have a different.
Yeah, but so that's what I was thinking, no? So in the end, you have a single stability point or a global minimum, which is given by the point in which one of the beams is no longer necessarily strong enough, not
Yes. Yeah, exactly.
to
And
counteract the other one,
that,
and I think
that's why it's important to have.
I also think it's very interesting.
Yeah.
Uh, Sorry, go on, go on.
Yeah, that was, I didn't mention, but it was important to have a separation between beam waste about 10 microns. If we change this value, we lose the stability condition.
Yeah. And also, I think the pitch of your washboard must depend on the radius of the particle. So that's why you have all these oscillations, no?
Yes.
But it's interesting that they look very regular when you see the videos in the bigger particle, the 5 micron.
Yes, exactly. Yeah, that makes a lot of sense. With bigger particles, they saw that, and yes, when we have bigger particles, they don't distinguish the minimal. They will just go on one direction or the other. But yeah, this is interesting, and also because.
But for example, here that you show, if you see this video.
Yeah.
So, so for example, if you show one of these videos, are you changing anything, or is just random motion from one minima to the other? I think not necessarily in this one, but the next one.
And yes, when they oscillate.
Yeah, this one.
Yeah, I think.
Yeah, is this random? Just
I'm not sure because we didn't analyze this. Actually, nobody liked these videos, only me. So for the other co-authors, they said, that's ugly. And I said, I think this is nice because.
Nice.
Yes, because also in this case, we expect some equilibrium. We don't have the equilibrium. We have unbalance. But it shows you that what you have is not standing wave. So, and also it shows you that the particles change the polarization state. So it's like having a quarter wavelet or half wavelet. So it's changing the polarization state, and that's why it's moving and is reorienting. So it's an active element changing the polarization, and it's not standing wave. But yeah, they said, no, this is too much, it's complicated, forget about it. But for me, this was the best or interesting. But at the end, it wasn't published. And because it was collaboration, um, yes, that collaboration is no longer continuing. So it's interrupted probably forever.
Okay, so I have more questions, but I guess we can ask them at some other time. If does anyone else have any questions? And if not, well, thank you, Raúl.
Thank you.
And I'll see you in the next. See you everyone in the next seminar.
See you.
Bye.